Hey there, Gen Chem students. I know that you're on spring break and you want to relax, but you've got that Chapter 15b Smart Work coming up, and the assumptions for equilibrium problems that we're going to be talking about right now will make your life a heck of a lot easier. So there's only 3 that we need to keep track of. Let's get started. The first one is the small k assumption. If you have an ice table problem and the initial concentration of that acid or base is much, much larger than the Ka or Kb, then you can ignore the X modifications to that original concentration. And the rule of thumb for that is the initial concentration has to be at least 1,000 times larger than the K value, or 10 to the third difference in the orders of 10. So for instance, if your initial acid concentration was 0.2 molar, that's 10 to the minus 1, and the K value was 10 to the minus 5th, that's a 4 orders of 10 difference. You could ignore the X modification in that case. On the other hand, if you had an initial concentration of 0.2 molar, 10 to the minus 1, but your K value was 10 to the minus 2, that's only a 1 magnitude of 10 difference. That's too close for you to use this simplifying assumption. If you can use this assumption, it means that you don't have to use the quadratic equation in most cases to solve for your X. All right, assumption number 2. This is the one for polyprotic acids. If the first K value, Ka1, is much, much greater than Ka2, that second deprotonation, then you may ignore the second deprotonation. We will typically be dealing with problems like that, but if you really do want to know how to handle both at once, I can show you an example. And again, if that Ka1 is over 1,000 times larger than Ka2, then that second deprotonation can be ignored. All right, assumption 3. This one has to do with reading problems. If the context of a problem somehow tells you that a particular reactant is constant in concentration, then you do not have to make any changes to it in your ICE table. You can ignore those X modifications. Some of the ways that this might be indicated is by saying something is continuously being added to the system, so a gas might be constantly diffusing in. A beaker or a student might be constantly adding more of a particular component, or there might be some sort of solid in the bottom. You're working in a saturated system, so as this dissolving component reacts, it gets replenished by more of the solid dissolving. So these are all hints you can look for that assumption. So those are the 3. So remember, the small k assumption, where if k is much, much smaller than the initial concentration of the acid or base, you can ignore the X modifications to that concentration. The second one is the polyprotic acids, where Ka1 is much, much greater than Ka2, letting you ignore that second deprotonation. And 3, sometimes word problems tell you that things are being continuously replenished, in which case you don't have to worry about modifying those with X's either in your ICE tables. So, happy problem solving, and I will see you guys in a week.